Hi guys, so today we're going to be taking a look under the hood of source maps. So source maps are something of a mystery to most people. They're found in many kind of web-based compilation scenarios, or most of them to be honest, ranging from type systems to web bundlers, but often the details of how they actually work is not completely transparent, and a lot of people are not very sure what's actually going on under the hood. So today we're going to be taking a brief overview of what they are and how to use them, and then we're going to move on to walking through the lower level mechanics by building our own compiler, which will generate some code and produce its own source map for browser compilation. So the plan for today, we're going to be taking an introduction to source maps and compilers. What is a source map and why they're useful? Using source map within popular tools. What is AST? Steps in transforming JavaScript. How compilers build source maps. And then for part B, we're going to be building our own compiler, which involves the first part of building a JavaScript code generator, then what is base64 VLQ, then adding source map support, and finally testing our source map. So let's get started. Part A, introduction to source maps and compilers. So let's first look at some reasons why people write JavaScript which needs translation into native JavaScript. For type systems, as you can see on the right, the list, there are ECMAScript features, so from 8, 9, and 10 of the spec. The problem is that in the process of turning these modules into assets, the code itself can become unreadable for humans, as the emphasis is put on the computer, which is usually a server or a browser to read. So we can see the usual architecture for a compiler is taking these modules, putting it through the compiler, and producing these assets. So an example code snippet is there, which has been put through a compiler, and you can see it becomes near impossible to reason about, and even harder to debug if there was an issue. So this is where source maps come in. So a basic definition for a source map is a source map provides a way of mapping code within a compressed file back to its original position in a source file. So it's fairly straightforward in its purpose. Modern browsers will parse the source map automatically and make it appear as though you're running un-minified or uncombined files. So an example below shows the TypeScript in the browser, something which is only possible due to source maps. So you can see we've got a breakpoint on line 14 there. With this, you can now inspect the call stack, the variables, and any kind of runtime state. And that's all via the pre-compiled TypeScript file, TypeScript code. So connecting the browser to your source map. So there are two ways to let the browser know that there is a source map available. The first way is at the footer of your file, having this comment, source map URL. And then the second way is within the header, having a header called X source map path. And again, giving the location of your source map there. So there are a couple of points to note, which is that Chrome will only download a source map if the DevTools is open, as they can be pretty huge in size. It's a big load for the user to download if they don't need to. Source maps will not appear as a network request, so inside of the network tab you won't see them. And once you have your source map, you can add breakpoints inside the source code, so that's found under the sources tab, as you can see at the image there on the right. So, brief look at some source map file contents. So currently, source maps must follow the latest spec, which they have their own spec, and it's in spec version 3, and you can find the full spec in that link, that Google Doc link there. It's mostly written by Mozilla and Google engineers, and version 3 comes with improvements to the overall size, so it speeds up things like downloading and the parsing. So the image that I've got there actually shows an example source map, and the important thing to note there is the mappings property. And these are all base64 VLQ strings, which contain the actual mappings from the source to the generated code. More on this later, as we'll be producing our own. So, usage in popular tools. In Node.js, using the flag enable source maps. And source maps are cached and used for stack traces when an exception occurs. So very useful for server debugging. In Babel, by default, Babel will add a source map location to the bottom of every generated bundle. As you can see where with the not inline part of what I've given there, but via the flag source maps inline, you can actually tell Babel to use an inline source map. So which looks like that first one there, which is it's a base64 encoded string of content. So it's much longer, but it doesn't require an extra file download. With Webpack, via the config property devtool source map, again it puts the comment in the bottom of your bundle. It's worth noting that because tools like Webpack often carry out multiple transformations using many different processes, at once. There you've got Babel and TypeScript, for instance, and it can still produce a single source map. So each processor will produce its own source map, and then there are libraries available which can concatenate the JavaScript files and consolidate the corresponding source map files. And this is what Webpack does internally. And you can also find some open source versions of this, where there's a library called mapcat, which does this. So, before we go much further, we need to take a quick look at one of the important mechanisms inside any JavaScript compiler, which is AST. So, AST stands for an abstract syntax tree. It's basically a tree of nodes which represent a program of code. A node being the smallest possible unit, and it's basically a POJO, a plain old JavaScript object, which has type and location properties. All nodes have these two properties, but based on the type, they can have various other properties as well. And in the AST form, code is very easy to manipulate, so operations like adding or removing or replacing, even replacing code, becomes much easier. So an example of AST is on the right. We can see at the top, we've got an example of some code, and then just below that is the AST that it produces. And there are websites such as astexplorer.net, which are great at letting you write JavaScript code and immediately seeing the AST it produces. So the important part of processing AST is understanding there are different approaches to doing this, and each has different pros and cons. And an example that we'll be looking at today is a popular one called using a depth-first search. And it works by starting at the root and exploring as far left as possible along each branch before backtracking. So it would process a tree in the order in the image of, the bottom left you can see an image, that's the order that it would process a tree. So you can see we've got a block of code here, which is the 2 plus 3 times 1, and it would produce the tree below that. You can see there's the tree of add number and then multiplication, the operations, and then the literals. So moving on to steps in transforming JavaScript, there are 3 steps. It passes the source code into AST, which there are 2 steps there, starting with lexical analysis, which is turning a string of code into a stream of tokens, so an array of tokens. Then syntactical analysis, which turns the stream of tokens into its AST representation. Secondly, is transforming the nodes on AST. So this is where we manipulate the actual AST nodes itself, and any library plugin would operate here. So for instance, Babel. And then generating source code. Here we take our AST, we turn our AST into a string of JavaScript source code. And today, that third part, that's what we're going to be looking at today. We're going to be looking at the jobs of the generator. So there are kind of 2 types of libraries that exist within the JavaScript world. One type that do all of them in one, which is you have things like Babel and Recast and Facebook code mods. And then the second type of library which just do one of the 3. So there's a Screamer, which is parsing, ast-types, which does your node manipulation, and then ESCogen, which does your generation. So how compilers build source maps. There are 3 parts to producing a source map within a compiler, all of which a compiler has to do. So it transforms the code and notes the new generated source location. It checks for a difference in the location between the original and the generated code, and then using these mappings, it then builds a source map. This is an oversimplification, and we'll get more into the nuts and bolts of this in part B in a moment. So on to part B. So now we're going to cover this spec in a lot more detail. So we're going to be starting with an architecture that looks like this, with the aim to produce a transformed file, which is the index.es5.js, and the corresponding source map. So you can see the index.es5.js.map after compilation. So we've got our index.es6.js, which will look like this. It's a simple add function, and then we assign that onto the global so it's available to be used. So now we have our pre-compiled source code. We want to start looking at the compiler. So come back. There are 6 steps to the compiler. There's the first step, which is passing the code into AST. And this video isn't going to be focusing on parsing. So we're going to be using a third-party tool to do this. The second step is adding a shallow clone onto each node on the AST. So this idea was borrowed from Recast. And the actual idea is that each node will hold itself as well as a clone of itself. So that's the original. The clone is then used to check if the node has changed. So more about this later. The third step is transforming. We'll be manually doing this, but we could use libraries such as ast-types or Babel types, as they have really clean APIs. More on this in a moment. Step 4 is generating the source code, so turning the AST back into JavaScript. Step 5 is adding the source map support. And 4 and 5 are kind of done at the same time. So this involves traversing the tree, detecting where the AST nodes have changed with its original property, and then for those instances, storing a mapping between the original and the generated code, and then finally using that mapping. And then the final part is writing to build. This is where we write our generated source code and the source map to the appropriate file. Right, so into the code, so into where we're going to look at these 6 steps now in a bit more detail. So using a third-party tool, I went for a simple one called abstract syntax tree. We're going to grab our file contents and pass them into the library's parser, and then get our source AST. Nothing complicated yet. So adding a shallow clone. So first we're going to define a function called visit, as you can see on the left, with its job of traversing the tree and executing a callback function on every single node. So here we're going to be doing a depth-first search, as we mentioned before. So for every node, it's going to execute the callback. Then it's going to check the property if there's a property location, and if so, it will return early. If it is the current if the current property is location, then it will check if the current property is an array, and if it's an array, it's going to call itself for every child of that array. And then the final thing is it checks if any of the properties are AST nodes, and if they are, it then calls itself with that node. So it's going to recursively call itself for children within the tree as it has to. So next we move on to producing our clones. As you can see the image on the right. So our clone original AST function reduces a clone of the node and appends that onto the original. So for our cloning, we're going to use object.assign, as you can see. So it's a shallow clone. So that's just going to copy the top level properties. The nested properties are still connected by pass by reference, so changing them will change the property in the clone. We could have used the spread operator here, as that does the same thing. And then we will do our comparison using just the top level properties, which are enough to compare the 2 AST nodes and determine if they've changed or not. Overall, our code here will return the same tree, except with the original property on every single node. So quite a straightforward job. So next, we're going to be doing our actual node manipulation. We will keep it simple. So we're just going to be swapping 2 nodes for our program. We will start with the number number plus 1, and we want to end with the 1 plus number. So you can see we've manually taken a clone and then swapped it with the right node, swapped the left node for the right node, and then put the left node back on the right node. And now that should be 1 plus number. However, the locations are going to be all wrong. We've also not used a very clean API to do this, which many libraries do provide. So we've just manually done this. So an example of using a library with a really helpful API is something like this. So this is ast-types. And you can see it's got a much more a cleaner API of doing it, and it's certainly safer, it's easier to read, and faster to develop with. So in general, most big compilers will use a library to help them do this, but as ours isn't very complex, it seems fine to do it manually. So onto our code generator. So usually code generators are typically housed in a single file within a big library, and they can be several thousand lines long. For example, the ES-CodeGen's compiler is almost 3,000 lines long, and that's actually on the smaller side. I've used much of the same code for our compiler, as most generators need very similar logic to process AST into JavaScript, except what I've done is I've only used what is absolutely necessary for us to process the code for our index.es6.js file. So what you're going to be seeing through our compiler is exactly what's necessary to process our couple of lines of code. So there are 3 types of code we have within our compiler. The first is here, which is the node processors and character utilities. So on the left, we've got the general utility functions used to process AST nodes, and it depends on the type. So for example, a function declaration will have an identifier, so we know we can use that. And then we will be building our source code. It also includes some current character constants. You can see there on the right. So for example, there's a space, there's an indent. They are called from our type statements, which we'll talk about in the next slide. I wouldn't worry too much about this logic right now unless you're planning on writing your own compiler. And most of this was borrowed from the ES-CodeGen library. but this is again just what we need. So on to the second type of code that we've got in our compiler, which is the type statements. This is an object holding functions which are tied to the AST node type. So each contains the logic necessary to process that AST node type and produce source code. So they're very important. For example, for a function declaration, it can, as you can see at the top, it contains all possible variations of arguments, identifiers, logic, and return types. And there is a level of recursion that is common here. And by that I mean a type statement might trigger another type statement, which might trigger another type statement. So again, like with the previous utilities, we have only used the necessary statement functions to process our ES6, our index.es6.js file. So it's fairly limited, but you can now see how much code is required just to process our AST tree of 3 to 4 lines of code, in addition to that of the above. Again, a lot of this code was borrowed from the ES Code Gen, so please feel free to ignore unless you're planning on writing your own compiler. So the final type of code within our compiler is going to be used to process the code statements, so kick off the tree processing. We're going to iterate over our program code, so each line of code, and start running our generator. This will now return an array called code, which contains every line of our newly generated source code. So this is going to be all JavaScript code in an array. Sorry, each line of JavaScript source string in an array. So finally, moving on to, we're going to skip step 5 for now and complete the core elements of our compiler. So for this step, we're going to be, if you ignore the top line and just focus on what I've highlighted in red, so we're going to be adding a source map location to our generator code, and we're going to be building this file in the next section. Then we're going to be producing a bundle for our generator code. So that's joining the array of code together, as you can see, and then copying the original code so that the browser can see it. And this is actually only one approach to this, and this is only because of the way that I've tested it, which we'll come to finally at the end. So, adding source map support. There are 4 requirements when it comes to building a source map. We have to store a record of the source file, store a record of the generated file, store mappings of the index and columns, and then display them in the source file using the spec version 3, as we mentioned earlier. Actually, for a quick win, we can use a library which almost every JavaScript code generator uses, and it's from Mozilla, and it's called SourceMap. It's brilliant. It actually handles pretty much every point, handles storage of points 1 to 3, as well as processing the mappings into base64 VLQ. So just a little reminder of what the source map looks like with the mappings highlighted. This is from earlier in the talk. And the mappings are all in base64 VLQ, which is what we're going to look at now. So what is base64 VLQ? So base64 solves the ASCII problem of handling languages which don't have the full ASCII character set. So base64 has a subset of ASCII which is easier for processing in different languages. So that's base64. VLQ stands for variable length quantity, and its job is to breaks a binary representation of an integer into a group of small blocks of variable bits. And so when we put them together, base64, the idea is that it's optimized to make it easier to have these mappings between big numbers and corresponding information in source files. So very useful that way. So a line of code is represented in a series of segments, and I've given an example here. So an example is the number 1 would be represented in 4 A's, which also produces 4 zeros. And you can see how each number corresponds to, correlates to an item in the segment. So we've got our generated code, we've got our source file, we've got the line number, and then finally on the right, the column number. And then I've just put in the final image here on the right, where this is how it would look if we were building a basic mapping in JavaScript of building this segment. However, this kind of code doesn't handle the line and segment separation, which can be quite tricky itself with semicolons and double semicolons. So it's more efficient just to use Mozilla's library to do this for us. So back to our compiler. So we're going to be using the Mozilla source map generator. And to make full use of this library, we're going to be creating a source map instance to hold and build our mappings from the library. But we're also going to initialize and store our local mappings. So at times when a node is changed, we're going to be building the location, then adding it to our local mappings and to the source map instance. So you might be wondering why we keep this local instance. and it's so that we have a record of the current location start and end points, as that's crucial for building the next location. Our source map instance will not be useful for us to use just for building the source map, so we still need a local instance that we can use ourselves as we progress through the program. So now we need a function which will actually handle updating these mapping instances. So this here is our build location function, and it handles all the location generation logic. So most libraries have a similar function, and the idea is that it uses offsets for the column and offsets for the line, which are given by the caller to then generate and produce new source map mappings. Its job is effectively to work out the new start of line and column numbers, as well as the end of line and start column numbers. And that's on the left, and then on the right you can see it will only add a mapping if the node has changed. So we're going to check the node against the original source of the node. So we're going to be limiting what mappings we actually store. And then the Mozilla mapping, that's us calling our mapping, our Mozilla instance writing to there, as well as writing it to our updating our location. Now we have our build location. We need to go about introducing it across our code, as well as adding it to our local instance. Sorry, we didn't actually add it to the local instance on our last function. A couple examples are here at the top, the left and right. So I've added it for the generate identifier code. You can see we build our location, and then we push that mapping to our mappings. So all mappings go into our local state, all locations with its start and end, but not all of them will go into our Mozilla source map instance. So I've added it here for our the generate identifier processor utility, and on the right the literal ast-type statements. So that's how we would incorporate our build location. We now need to apply this throughout our code generator. So all node processors and ast-type statement functions need this. I found this quite tricky actually, as the node to character mapping is not quite always one-to-one. For example, a function could have brackets either side of its argument, which has to be accounted for when it comes to the character line positions. So you can see that with the brackets would have different character positions to without the brackets. So tricky problem. So what I found is that most libraries introduce logic and defensive checks using information on the AST nodes, so that all scenarios can be covered. And I would have followed the same practice, except I was only adding code for what was absolutely necessary for our index.es6.js code. So I'm not going to show the presentation all the times we've added build location. You can see if you go to my repository that I've linked at the end of this presentation, all the locations where I've added the build location. So you can see how much code it adds and where all the complexity is there. So the final part is writing our source map contents into the source map file. This is surprisingly easy with Mozilla's library, as they expose this toString method, which will handle the base64 VLQ encoding and build all the mappings into our v3 spec compliant file. So really nice. So it makes it really easy for us. Now we've got our now the reference to index.es5.js that we added earlier, as we can see when we added the source map location. Now the file actually exists, so that's great. So our compiler is now done. That's it for the compiler. So we've now completed all 6 steps. So how do we now get confirmation that it's all worked? So testing our source map. So if we compile the code, we should produce our build file with these 3 files inside. So that's the original, we've got the index.es6.js, the generated file, which is the index.es5.js, and the source map, which is the index.es5.js.map. There's a really fantastic website called Source Map Visualizer, which I've put the link there, which lets you visualize source map mappings. So the page starts like you see on the right, so it's just empty. And what you can do is you can just drop all of your source files into it, and it now becomes the bottom. So very colorful, right? This contains the original code, the generated code, and the mappings decoded. So you can see the mappings decoded there at the bottom, the original, the generated and the source code slightly higher up. So a little reminder of our transformation from earlier. We swapped the number plus 1 into 1 plus number. So we now want to confirm that this mapping has worked. So if I hover over the character of the mapping, it will highlight the mapping and its corresponding locations in the generated and the origin location. So it's really great at showing you these mappings. So the top screenshot shows what happens when I hover over the literal number 1 character. It clearly shows the mapping with the generated, with the original, as well as the mapping. And then the bottom screenshot shows what happens when I hover over the variable identifier number, which is the word. And again, it clearly shows the generated, the origin, and the mapping. So all works. Fantastic. So what are the limitations of building a compiler like this? So there's a couple. So obviously not all JavaScript statements were covered. So we only did what our code needed, and it was still 130 odd lines. Currently it only works with one file. So web bundlers will follow the app building and dependency graph and apply transformations on those files. There's actually a lot more on this in my Under the Hood of Web Bundlers article and video. So feel free to click on that if you're interested more about how web bundlers build up a dependency tree and then use that. Third point, the output file versus the bundle. So web bundlers produce bundles with code runnable in specific JavaScript environment. Ours doesn't think about this, so ours is very limited. Again, for more information on how web bundlers produce this code runnable in specific JavaScript environments, see my Under the Hood of Web Bundlers talk and blog post, because it goes into detail on how it produces that kind of JavaScript runtime environment. And the final point is it's only doing basic transformations right now. So it's not performing any additional optimizations, would not really be easy to do without us adding a whole load of new code. So that's a lot to take in. Thanks very much for watching. This topic was really far-reaching. I learned a huge amount in researching it, and I really hope that this serves as a bit of a light on how JavaScript compilers and source maps kind of work together and the mechanisms that are kind of involved. The source code is all available for look at my Craig Taub our own Babel source map repository. I hope please spare a like if you enjoyed this, and stay tuned for more soon. Thanks so much, guys.